Hello, I'm Frederick.
And I'm Aiden.
And this is Team Fusion Zero, participating in the RoboCup Junior Rescue Line Division. So, a bit about the team. I'm Frederick, and I am the team captain, lead CAD designer, and I focus mainly on the physical structure and solving problems on the hardware basis first. I've been doing robotics since 2019, and have achieved podium places in both Auckland and New Zealand competitions.
I'm Aiden. I primarily focused on the line following and software side of the robot. I've been doing robotics since I was 11, and I've come first in New Zealand through rescue line and online competitions.
Our team naturally formed as people came and went, and we've both been competing together since COVID within the international rule set.
Recently, our team placed second in international competitions at RoboCup Australia and RoboCup Singapore.
So let's start off with the robot overview. We derived physical constraints and goals from the rulebook and our own experiences. We've seen how other teams struggled when their robot was too large. Thus, a main priority for our design was to minimize the footprint as much as possible. To achieve this, we have utilized 3D printing with CAD, creating custom PCBs with easy EDA, and recreating a wheel. Let's go over the main components on board. We use the Raspberry Pi 4B as our main processor, and only the Raspberry Pi. This is because we have created our own custom 40-pin header shield. It provides JST connections for a sensor stack, PWM pins for motor control, and digital outputs and inputs. To power all of this, we use two 18650 batteries. Our drive chain consists of 4 PDI 6221MG continuous servos and are controlled with PWM signals. To create a two-stage claw, we used the RDS3218 as the claw lifter. Additionally, the SG90 acting as the closer for the compartments. To generate the PWM signals required, we used a PCA9685 chip. To read analog signals, we used the ADS730 from Adafruit. Some important sensors that we use are the GY-BNO8X, which is a 9-axis IMU. Furthermore, we use TCRT 5000s. We use this in both our color sensor board as well as within the claw for both line follow and victim identification and verification. Finally, for this competition, we introduced our new wheel design, the WEG. Made from silicon and PLA filament, it can achieve great grip within inclines. The incomplete circle leaves notches that are able to directly hook onto speed bumps, allowing us to gain a mechanical advantage in lifting the robot past difficult terrain. Our design process is iterative. We identify issues with our hardware during any testing phase, then iterate on it through the parametric design system of Onshape, and finally print and assemble quickly with 3D printers. The hardware used for the line following includes a downwards facing Pi camera module 3 with LEDs. We use limit sensors and TOF sensors placed on either side. Finally, the IMU allows us to generate what we call modifiers that indicate whether we are going uphill, downhill, tilted, or we are passing a seesaw. The hardware used for the evacuation zone are the forwards-facing camera and side and front TOF sensors. Finally, our custom two-stage claw is built in such a way that it does not rely on external conditions, as it is a top-down claw design.
Moving on to software, starting with line following. Each loop starts by reading inputs from all the sensors: the front touch sensors, the rear color sensor, and the main camera. What happens next depends on what the robot sees. If the silver isn't detected, the robot continues line following as normal. If the red appears in the camera frame, that usually means the finish line, so the robot stops. If one of the front touch sensors is triggered, it switches into obstacle avoidance mode. In obstacle mode, the robot first drives forward until both front sensors are pressed, confirming that the object is directly in front. Then it follows a detour pattern, starting with the center sensor and using the side sensors to guide around the object. Once the rear color sensor detects black, it realigns with the line and continues. For black line tracking, the robot finds dark contours in the camera and filters them using a series of checks. First, any valid contour needs to be at least 1000 pixels in area. It also must extend far enough down the image to be close to the robot but not touch the very bottom. Anything too far to the sides or too short is ignored. If more than one contour passes these checks, the robot picks the one that's tallest and has the largest area. If the robot doesn't see any black contours, it assumes this is a gap. It moves backwards until it sees a black contour, and then adjusts itself until it is around 90 degrees. To find the next line, it moves forward a set amount of time, and checks if there is a contour. When green is detected, the robot prepares a turn. If the green is too high up in the frame, it waits until it gets closer. Then it checks whether black is present just above the green. If both sides have green with black above, it's a double turn. If there's only one green, it looks to the left and right for black to decide the correct direction. These check areas are marked with the yellow circles. To steer, if green isn't involved, the robot calculates the angle of the black line using the top and bottom points of the selected contour. If the top point is unusually low in the image, it treats it as a sharp curve and turns more aggressively. It adjusts wheel speeds based on the angle to follow the line smoothly. Now, moving on to the evacuation zone. First, the robot checks its claw to decide what to search for: live victims, dead victims, or a triangle. To find targets, it scans the field. Live victims are detected using their bright reflective highlights, and dead victims are found using hue circles and their dark colors. Green or red triangles are found based on color as well. Once a target is found, the robot routes towards it by adjusting its motor speeds to stay centered on the object. For picking up victims, it centers itself using its laser sensors, then sweeps and fine-tunes its position before grabbing. If it fails, it repositions and tries again. For drop-offs, the robot brings itself away from the evacuation walls before finding the triangle and dumping the correct victim.
In the future, we wish to implement some changes, including full mapping with the SLAM model within the evacuation zone, incorporating and running artificial intelligence in parallel, such that we are able to use our current method alongside AI for further verification. We would wish to upgrade to a Google Dev 1 Micro, as would also allow us to use much more processing power.